Hello everyone and welcome. My name is Jeremy Wallace. I'm a Specialist Solutions Architect in Robotics here at AWS. I'm joined by my colleague and fellow Solutions Architect in IoT, Massimiliano Angelino. We're excited to talk about how to manage robot fleets using AWS. So today we're going to walk through how to reliably deploy and launch applications on robots. Then manage and monitor your robot fleets using AWS. We prepared a fun dancing robot application to use today, which we built using the common robot software framework ROS and the NVIDIA JetBot. So we'll start off with an overview of the common challenges customers face when managing robot fleets. Then we'll give a brief introduction into the ROS development cycle and how to package ROS applications for deployment. Next, we'll highlight how customers can use AWS IoT Greengrass 2.0 to reliably deploy and launch ROS applications. Then, how to use Fleet Hub for AWS IoT device management to visualize and manage your active robot fleets. Along the way, we'll show you how this works by deploying and launching our dance application on a global JetBot fleet. And of course, we'll end with an international robot dance party. So managing robot fleets is a challenging task, especially when they're in remote locations. Seafloor Systems has been building surveying solutions for hydrographers by hydrographers for over 20 years. They currently have hundreds of unmanned surface vessels, or USVs, that survey every water body, both inshore and offshore, around the world. Managing their fleet of field-deployed USVs at scale is a difficult task. So when provisioning and deploying new software to robots, Seafloor Systems ran into common challenges that robotics companies face. Keeping the robot software up to date often required costly visits by on-site technicians, and that could take days to weeks. Using AWS IoT Greengrass 2.0, Seafloor Systems enabled operators in the field to reliably deploy new software and onboard new USVs in minutes without requiring local technicians. So over-the-air updates is only one of the common challenges that customers face when building solutions to manage their robot fleets. The difficulty of setting up a secure communication layer between the robot and external systems often prevents customers from leveraging the full benefits of the cloud. Running operations on robots, from starting missions to troubleshooting problems, usually requires some on-site technical expertise. Finally, understanding the health and current state of your robot fleets is critical to making operational decisions. It's challenging for companies to set up highly available and scalable dashboards and alerting workflows to catch problems before those problems cause issues in your production fleets. Today, we're going to highlight how you can use AWS to get those over-the-air updates onto your robots without having to have on-site technicians. We'll discuss how to securely connect robot applications to external applications that could be running in the cloud, how to run remote operations, and how to set up highly available and scalable robot fleet monitoring and alerting infrastructure in minutes. But before we do, let's do a quick primer and introduction into the most widely used software framework for building robot applications, ROS. ROS is a flexible middleware software framework for building robot applications that was designed to encourage collaborative robot application development. It contains a collection of tools, libraries, and conventions that make it easier for robotics developers to build sophisticated applications. The common development lifecycle for robot applications usually starts with simulation. Simulation enables all developers to easily access virtual robots to test applications and algorithms without requiring access to expensive and scarce physical equipment. AWS RoboMaker enables developers to quickly run simulations in the cloud with a simple API call. RoboMaker can be integrated with automated test workflows and CI/CD pipelines. While we won't talk at depth about the structure of ROS applications or simulation today, but please check out our comprehensive guides on our AWS RoboMaker website under resources to get more information. So developers will commonly iterate many times in simulation before deploying to physical robots, and that second half is what we're going to focus on today. How to reliably deploy software to both local test fleets and then eventually your production fleets using AWS Greengrass 2. So before we jump into Greengrass, you'll need to know the build and bundle cycle for ROS applications. ROS applications usually comprise of multiple packages within a workspace, which is how software is organized in ROS. Colcon is a tool that will build all your ROS packages in your workspace and prepare an installation package that will end up on your robot. Colcon Bundle will then create a single and portable tar file that includes both the installation package for your application as well as another tar file for all the system dependencies. And so these tar files that get bundled with Colcon are supported by AWS RoboMaker in simulation in the first half of the ROS development lifecycle. So we use the same mechanism today to package and deploy our ROS applications along with all the dependencies to our physical robots. While Colcon is not required for ROS application deployment with Greengrass, you could use containers, you could use your own custom packaging mechanism. Colcon is a convenient packaging mechanism and enables easy integration with those simulation testing workflows in RoboMaker. The output.tar file contains two separately packaged overlays, one for the ROS distribution and any of your system dependencies, and then one for that built workspace. These overlays can then be reliably deployed together as individual components within Greengrass. Within the component configuration, which we're going to dive into shortly, you can leverage ROS launch using the ROS package name and desired launch file, then to easily start your ROS application locally on the robot. So to deep dive and walk you through how this works in Greengrass, I'm going to pass it over to Massey.
Thanks, Jeremy. I am excited to be here today to explore how Greengrass can enable and simplify fleet management for ROS application. My name is Massimiliano Angelino, and I am a specialist solution architect in IoT. I had the chance to try out Greengrass version 2 in beta, and would like to share these new features with you. First of all, let's introduce Greengrass for those of you that might not know it. Greengrass is comprised of a client software running on the device and a cloud service to manage these devices. Greengrass enables the device to perform local tasks without the need to continuously exchange data with the cloud, reducing latency and allowing for scenarios where the device might be disconnected for a long period of time. It also manages over-the-air updates of both the business logic and of the Greengrass client software, ensuring ease of management and agility and longevity for your robotic devices. AWS Greengrass has the same security mechanism and encryption using the cloud with AWS IoT, and allows for your code to interact with all the AWS services in a secure manner without having to bother about credential management. Let's now look at the enhancement introduced with Greengrass version 2. In particular, we will focus on how Greengrass helps in managing fleets of robots at scale. To start with, Greengrass 2 client software is written in Java in order to benefit from the extensive platform support of the Java virtual machine. Greengrass version 2 supports the execution of arbitrary code packaged in self-contained components. Components provide a flexible way of describing what Greengrass should run and introduce advanced features such as lifecycle management hooks and dependency management to simplify how software is developed and deployed. Lifecycle hooks allow a fine-grained control of how the software is installed and executed on the device. Components adapt to the way that you write code and not the opposite. Components support your preferred runtime such as Golang or Rust, or platforms such as ROS. Components can also be used to run containerized applications with Docker, Docker Swarm, or Kubernetes. Lambda support is provided by a specifically Lambda component and ensure compatibility with Greengrass version 1. Components make Greengrass more flexible, enable more use cases than a Lambda-only approach, as we will demonstrate later. With Greengrass version 2, you can develop your component locally, deploying them directly to the Greengrass runtime on the device without needing any cloud round trips. This speeds up the development cycle by a substantial factor. Once the code has been verified locally, it can be uploaded as a cloud component and made available to the rest of the fleet. This can be done using the CLI from the edge device or by committing the code to a source control system integrated with a CI/CD pipeline. Finally, this is probably the most important feature introduced by Greengrass in relation to fleet management. Greengrass version 2 directly integrates with the thing registry and AWS IoT jobs. Greengrass devices can now be part of theme groups, and a single device configuration can be deployed to thousands of robots belonging to the same theme group. AWS IoT jobs makes it possible to leverage advanced features such as rollout speed, control, and automatic abort. Let's now have a look at how these features can be used to deploy a ROS robot onto a fleet. The first step consists in defining a recipe for the component. This recipe contains the information necessary for Greengrass to obtain the code, install it, and run it on the device. A recipe defines the version of the component, configuration parameters, dependency of these components, artifacts, and scripts on how to run this code on the device. As Jeremy showed before, ROS application packaged by Qualcomm Build consists of two archives, the dependencies and the workspace. We can then create two components, a ROS component containing the workspace, so the dance bot, and a dependency component for the ROS core. We then make the ROS component a dependency of the dance bot component in order to ensure that it will be available whenever we deploy the dance bot. In the dance bot run script, we can then source both dependencies and the workspace as we do usually with ROS and invoking ROS launch. The next step is to actually create a deployment containing the dance bot component targeting the theme group representing the fleet of robots. In this stage, we can also override some of the configuration parameters defined by component. For example, a topic where the robots listen to get the commands. Finally, as AWS IoT jobs deploy this configuration to the fleet, it is received by the Greengrass client running on the robots, which downloads the artifacts and executes the lifecycle scripts. In order to get there, though, we must first install Greengrass on the robots. Let's see how. Greengrass version 2 provides an easy setup mode for development purposes and supports a large-scale provisioning workflow for production. We will show the development installation mode in the demo. But if you're setting up a production system, you can leverage certificates and other fleet provisioning features of AWS IoT. For example, you can use secure element to secure your credentials. Greengrass can also be pre-baked into the OS image running on the robot or installed using tools such as Ansible. Talking of production fleets, one concern the customer raises is the ability to have deployments that are reliable and aware of the edge state of the devices. Greengrass version 2 leverages IoT jobs features such as configurable deployments rates and failure thresholds to implement strategies to address a limited set of the fleet to verify the deployment works before addressing the remaining fleet in bulk. This can also be combined with the timeout settings in order to detect unreachable robots. On the edge, Greengrass can detect if the component has been deployed and execute together with additional custom verification. Components installation and execution is retried in case of failures and rolled back if not solved. Finally, Greengrass version 2 exposes also some hooks to do environmental validation for the robots. For example, you don't want to deploy a new update in case the component is performing some critical activity or if the battery is not sufficiently charged. So with this, enough with slide, and I hand it over to Jeremy to start with a demo about how to install the components on via ROS and Greengrass version 2.
All right, in this demo, we're going to deploy a dance application to our NVIDIA JetBots. So we'll start out with a development environment in the cloud. To do this, we'll open RoboMaker, click on Development Environments, and then create a new development environment. For today, I already have a development environment we can use. So we'll go ahead and open our development environment. Once we're in our development environment, we prepared a sample application that we can use today that will enable our JetBots to dance. The first thing you'll notice is both a robot workspace and a simulation workspace. It's a common practice to simulate your code before deploying it to a physical robot. The simulation-specific code, 3D models, sensor emulation libraries, etc., are stored in the simulation workspace. To learn more about how to run RoboMaker simulations, check out the RoboMaker resources page on our website. Today, though, we'll be working in the robot workspace, which contains the code that is deployed to our actual robots, in this case, our JetBots. In the robot application, you'll find a dance ROS node. So this node will parse a YAML dance routine file with an array of dance steps. Let's take a look at one of these dance routine files. This dance ROS node will publish a set of commands over a ROS topic to another ROS node that will then move and actuate our robot. Once running, the JetBot will complete the entire dance routine. We will invoke both the dance node and the node that actuates the motors using a simple ROS launch file. You'll notice these ROS launch files in the launch folder. The first step is to run the Colcon build and bundle commands. Since the JetBot uses an NVIDIA Jetson Nano, which has an ARM64 architecture, we'll run these build commands in a Docker container to cross-compile the application. We've set up a script here to make this easy. So in this script, first we're just updating our sources lists. Then next we will update ROS dependencies, or a tool called ROS deps. And then finally we'll run the Colcon build and Colcon bundle commands. Once the application is built and bundled, we can now copy both of these tar files into an S3 bucket and stage them for deployment. To make deployment as easy as possible, we're going to use Greengrass. First, we'll define two components, one for each of the layers that Colcon just created for us. A component is specified via a recipe, or a YAML file containing information such as the component name, its version, and any component dependencies it may have. This file includes configuration parameters such as a name or an endpoint, and a list of lifecycle hooks defining what to do to prepare the environment and run our component. The first component we'll create is the base ROS melodic component, which is packaged in the dependencies tar file built from Colcon. Great. So once we've created the component, it is now ready to be deployed. Next, we'll create the component for a ROS dance application. In the run stage in the application lifecycle, we will first source the dependencies overlay from the required base ROS melodic component. Then we'll specify a couple environment variables, including the IoT endpoint to use and robot name, and finally we'll use a ROS launch command to start the application. Just like the base component, we'll define the artifact Greengrass we'll download and install. In this case, the built workspace tar file from Colcon. So once our two components have been created, we can go ahead and deploy the code to our robots and test that everything works as expected. So now is a good time to pass it over to Massey, who's preparing some JetBots in Sweden.
Thank you, Jeremy. Let's start where Jeremy left over. Here we see the components he just created, the ROS melodic and dancebot, together with some others that I created earlier that will come handy when we deploy the full robot functionality. Here we can also see the core devices. At the moment the list is empty, but I have 5 robots that are waiting to be onboarded. So let's see how to onboard one of them. Here I'm connected to one of these devices through a shell terminal, and I already have downloaded the Greengrass software. What I need to do next is to unzip the archive into a folder. What I to do next is to use this command that you can find in the console that I copied for convenience. What this command do is installing the software into the right directory on the device, and at the same time is also provisioning the cloud resources that are necessary for Greengrass to connect and be provisioned remotely later. This is done by specifying the flag provision true. In addition to this, we're also setting up Greengrass as a system service in order to have it run every time we reboot the robot. The installation is now done. The next thing before going to get and create the deployment, we are going to take the logs to see what happens under the hood when we are going to deploy components to this device. Let's now create a new deployment. So here we provide a deployment name. And we select the theme group to which my robot belongs to, and the same theme group will be used later by the robots in the fleet. Here we're selecting which component we want to deploy to this device, and in this case it will be a dancebot. We can also select some of the public components, such as an SNS or Fyros or other that are provided by Greengrass, which can be used to enhance the functionality of your robot. We don't do that at the moment, so we just click Next. At this stage, we can configure the component that we have chosen. In this case, for the dance bot, we could change the mode on which it's running. At the moment, for this first robot, we will use a demo mode, so that when the component is deployed, the robot will start dancing. Otherwise, in production, we will turn this off and let all the robots start at the same time. In the next screen step, we can select additional configuration for the jobs. We'll skip it for now, and then we confirm the deployment. Going back to the Jupyter notebook, we'll see that this job is being received by the robot, which will then download the components and launch them. As you can see, the robot has now started dancing. So while I'm going to onboard the other 4 robots, I give back the word to Jeremy that will guide you through how to monitor a fleet of robots through a service called FleetHub. Jeremy?
Now we have at least one robot dancing, but before we get the rest of the JetBots to join the troop, let's talk about how we can easily build robot fleet dashboards using FleetHub for AWS IoT device management, which is available in preview today. So FleetHub for AWS IoT device management is a fully managed web application for customers to build rich operator dashboards in minutes. With a simple interface, robot operators can visualize their fleets, filter and search through robot metadata, set customizable alerts on current conditions, and then take actions on individuals or groups of robots. FleetHub provides a single pane of glass view on the state of your robot fleets, enabling you to quickly identify and take action before a production issue occurs. The best way to learn about FleetHub is to get hands-on, so we're going to jump into a quick demo. Okay, so the first thing we'll do is go ahead and open up FleetHub. In this first window, you'll see a list of FleetHub applications. So what's nice about FleetHub is you can actually create multiple applications, each with different views for different robot operators or different teams within your organization. Today we've prepared a FleetHub application that we can use to visualize the state of our dance bots. So let's go ahead and open up this application. So now that we have our FleetHub dashboard open, you can see a few different things. First, on the left, you'll see a list of all the dance bots that we've provisioned. And as you can see, not very many of them are online. This is because these robots are not actually turned on right now. Next over here, what we can see is the last known reported battery, as well as the last known reported city of where these robots live. You'll notice we have robots both in New York as well as Kungsar. So I guess the first thing we'll have to do is go ahead and turn on these robots. So I'm going to go turn on these robots. Okay, so as you can see now, all the New York robots here are online. Now let's say you want to be notified when one of these robots enters a state of low battery. And so in this case, let's say we want to create a new filter. And on that filter, let's say we want to select the battery level. And let's say we want to check when the battery level is below 11,000 millivolts. So you'll notice that 2 of our robots here in New York have entered a low battery state. This may be an important piece of information you might want to alert your team, your robot operators, to let them know that the battery is running low. To do that, we can create an alarm. So we'll go ahead and press Create Alarm. You'll notice that it took our filter here where we defined that to include all robots that have a battery level of less than 11,000. In the next section here, you can choose how we want to aggregate the data that's generated through this metric. So in this case, let's just count the number of robots that are currently in a low battery state, and we'll choose a period in which the frequency in which we're going to alarm to be 5 minutes. In this next section, you'll be able to set a threshold. So in this case, what we could say is we want to get an alarm when, let's say, 2 of our robots are less than this value and therefore are at a low battery state. We can create an email list name as well as a list of emails that will then receive this notification. Keep in mind, this kind of thing can be easily integrated with tools that you may already have for alerting, things like PagerDuty. So we'll call this robot operators, put in my email address, call this name, alarm name, battery level low. The fleet has reached a threshold of 2 robots at low battery. So we'll go ahead and press next. We'll review, and then we'll go ahead and submit. So now we'll get an email alert when our threshold of more than 2 robots within our fleet are at a battery level that is low. All right, so now we've confirmed that my fleet of robots are live. I'm going to pass it over to Massey, who's going to describe what's going on Greengrass, how these applications are then going to be deployed, and then we're going to start dancing.
Okay. Thanks, Jeremy, again. Let's look into the devices now. Now you see the full fleet, and what we have deployed so far to the fleet, it's the DanceBot and the monitor component. The monitor component we talked about before is one of these additional components we can put on the robots, and it works alongside with your robot in order to collect some information from the device, in this case, the battery, and it derives also the location based on the IP address. We also had described before another component, the bridge, and this will help us in actually controlling all these fleet remotely. And we're going to deploy it right now. So what do we do now that we have the full fleet online? We are going to just revise this deployment and adding a new component. So here are the 2 DanceBot and monitor. We see here the bridge coming up. So we select it. Here we see the new configuration with the bridge, the DanceBot, and the monitor now. And the ROS melodic, so the ROS components and the dependency will be automatically deployed because they are a dependency of the DanceBot. So I don't need to select them explicitly in the deployment. So I click next as before when I did it for one single robot. Now, since they are targeting, again, the DanceBot group, all the robots that we saw before will get this. So now we are deploying, and it will take a few minutes for the robots to get and download the component, install it, and run it. Okay, now a few minutes have passed, and the robot should have the components installed. So what we do next is to publish a message on this MQTT topic, dance demo. What will happen next is that this bridge component that we deployed on the device will get this message and translate it into a ROS topic message and deploy it and send it to the JetBot app, to the DanceBot app, sorry, and then start a dance. So here we're saying I want to start an autumn Vivaldi dance and at a specific timestamp.
Here we go. Is this the moment of truth? Ah, there they are.
All of them.
We're dancing.
Cool. I just have to watch in my other video. Cool.
We have a couple stragglers, but generally I think they're doing pretty good.
They needed some more training, maybe. Next time we'll add some AI ML to these robots, so maybe they can dance better. Oh, but that was great, I think.
That sounds good. That was an exciting dance. All right, so now we got our international dance troupe of JetBots doing their dance. Let's quickly recap on what we learned today. Today we discussed how to reliably deploy and manage applications on robots using AWS Greengrass 2 and Fleet Hub for AWS IoT device management. This covers that second half of the robot software development cycle after your test and simulation are complete and the robot application is ready to deploy to your physical robots. Using AWS Greengrass version 2, you can reliably deploy software components over the air with dials for deployment rates, failure thresholds, timeouts, and more. You can configure granular access controls to interact with cloud-based applications, and you can configure deployable components to run remote operations and troubleshooting tasks. With Fleet Hub for AWS IoT device management, you can set up a robot fleet monitoring operator dashboard in minutes and then provide field teams a single pane of glass view into the state of your robot fleets while setting up alerts to prevent downtime and schedule maintenance. So to get started with this solution and more, including a collection of open source ROS tools, sample applications, and cloud extensions, please check out our links to our blogs, documentation, and GitHub repositories. So thank you so much, and we'll see you next time.